All right, let's have a start. We're up to 16 people. That's about halfway there. It's pretty good for week 6 or 7 in the COVID quarter. Can you all hear me? Any sort of sign of life? Cool. Thanks, Ryan. So, a couple announcements. I launched a new homework, and I just wrote it last night, so it might be kind of rough. I haven't even, done it myself, but it's a really interesting one. And so it's going to look at replacing the city of Bainbridge, which is Bainbridge Island, basically, replacing their vehicle fleet. So the city operations and parks and police and that sort of stuff with all electric vehicles. And you'll ultimately have to, you'll ultimately have to compute a MAC. And so it's pretty involved. And I made the cover sheet. Let me try to just pull it up on my computer. Much more hand-holdy just because the data is insane. So here's the cover sheet. And on the top, we have all our baseline things that we need to calculate, like how much fuel is used per year with the internal combustion vehicles, energy costs, capital costs, maintenance costs, and then similarly for the project, replacing all the vehicles. So it's like two motorcycles, 52 passenger cars, 6 trucks, and 4 heavy trucks. And these are all their vehicles here. I've already done some of the preliminary analysis and averaged some of the capital costs and things like that. But have a look at the homework. Everything you need will be on this cover sheet or in the PDF of the homework. And we'll work on it again Thursday all together. And it'll be due like a week from now. But it should be pretty fun. And you all should start to be getting kind of used to this analysis. It'll be more the same, just a little bit more realistic and more in depth. And after this one, I think you'll have enough tools to really start thinking about a project and getting to work on a project. And maybe you'll have a few more ideas after this lecture. What else do I want to talk about? Some people can't get the Zoom videos overseas, so now everything is up to date on YouTube. You can watch those. It looks like some people are watching some of them. There's 5 views on the last lecture. So there it is. And that can be found on, let me hide those video controls. That can be all found on Canvas up here. So YouTube playlist of lectures and study sessions underneath the logistics module. Okay, so now we're into transportation. We did buildings last week or two, and I just posted the lecture. There's this nice little fact sheet from NREL, and then I link in the lecture to several EPA fact sheets for emissions for different fuels and that sort of thing. There's this green transportation video from grist.org, and this was done by Jesse Nichols, who graduated from Western a couple years back, and so now he's a energy climate journalist for Grist, and he did this nice article aimed at high schoolers, but I think it should be good reading for anybody in the world. Some of the math looks very familiar. It looks definitely like it came out of Institute for Energy Studies professors, right? Like the same sort of unit analysis we do here at Western. But there's a good video on walkable cities, which could give you a good project idea for this class. Bikes, another good project idea. Trains. And so have a look at all that in your free time. It's linked again on Canvas under the transportation module. All right, that is it for logistics. Basically start thinking about your project. I don't know how many more homeworks we're going to do just because I want to spend time actually working on these projects. And so I think I'll do one more lecture on utilities next week so we know how much emissions come from making electricity and how to reduce those emissions. And then maybe we'll do a lecture on land use, even though I don't know anything about that, but it could be more of an interactive lecture, I suppose. And then we'll get onto the project. I'll probably start announcing the project next week just so we have an idea. But if you want to get a head start, you can look at some of these things I've posted here, and maybe I'll post the actual project assignment so you can see what you're responsible for. Again, everything's low key this quarter, no stress. Do what you can, right? All right, on to the lecture. I got the chat open, so please chime in if you want to. How do I get rid of that dual slideshow? Oh well, I'll just let it go live. Hide presenter view. There we go. Okay, so this lecture will look at quantifying emissions from transportation. A lot of the equations are similar to what we've done so far, so this should be a shorter lecture and more just confirmation of what you already know how to do. Okay, so here's the big US greenhouse gas emission flow chart. Transportation's responsible for 27.2% of our emissions. Of those, 21% of overall emissions, so the lion's share of that 27%, is all due to cars on the roads. Cars and trucks, but mainly passenger cars. A little bit from air travel, and then a little bit from rail, ship, and other transportation. Zooming in on Washington State, our transportation budget for greenhouse gases is much larger. It's 42%. So you can see there's this big component of aviation and on-road gasoline. Why might that be? Any guesses? You guys can type in chat or speak out loud. Why do you think Washington State has such high transportation emissions? It's not necessarily high on an absolute sense, but high on a relative sense, on a proportional sense. So compared to like electricity emissions, for example, or heating yeah, so there you go. A few people are saying we have much lower electricity emissions because we have buses instead of subways. Yeah, that's definitely a component for Seattle. Temperate climate, there you go. That's a big thing. So it's Goldilocks here, right? It's not too hot, not too cold. And so we don't spend a lot of energy heating or cooling our homes. The last thing is our geographic location, right? We're on the sea and we're on a border with Canada. So we're a real trading hub. We're a port state. And so we have a lot of, and we have Boeing. So we have a lot of aviation, a lot of shipping going in and out of our state. And we have a lot of goods to sell and a lot of goods to purchase because we're also a relatively wealthy state. So transportation plays into all those things. Cool. Zooming in on Bellingham, our transportation is also larger than the US average. I don't have the absolute emissions here, but these are relative percentages. A lot of our transportation comes from our ports and also being on the I-5 thoroughfare between Vancouver and Seattle. So we have a lot of truck traffic going through our town that we're not necessarily responsible for, but it does go through our city. And this is from the Climate Action Task Force plan. And to our chagrin, we can't really influence that truck traffic, right? That's outside of any sort of city climate policies. We could do something crazy like put a toll where you enter and exit Bellingham, but I think that would cause some consternation, right? People would be politically upset with that. All right. Overall emissions for Bellingham is 100,000 tons. 100,000. This is 1 million metric tons. 1,000. What the hell? 1,000,000. Yeah, 1,000 K. So this is about 1 million metric tons for the city of Bellingham. So again, 1/3 of that or so is from transportation for our city. Don't pay too much more attention to this graph. Some of this stuff certainly I don't think will be achieved, unfortunately. Probably somewhere in the middle here. This initial dip from 2006 to 2012 was probably due to the recession. So if we do lose some emissions, it'll be due to COVID. Oh, a note on that. I'm seeing so many newspaper headlines like emissions down by 7%, 8%, projected emissions for 2020 down by 10% due to the economic hit that COVID's causing. That's good, but we're not out of the woods by any means. We just hit 419 parts per million yesterday in the atmosphere. And that's a total record, almost near 420. Party on, but it's still growing, right? Every year we emit, it's still depositing more carbon dioxide into the bank that is the atmosphere. And I think we're at like 39 gigatons of carbon per year, carbon dioxide per year. And 19 or 2000 levels was like at 29 gigatons of carbon dioxide per year. So it's 7% off 39. We're still like, really, really high. We're still at like 2015 levels. So we're still putting way more carbon than we actually need to into the atmosphere. And yes, coronavirus caused a small dip, but that dip we're still at levels way higher than 2000 levels. So we have a lot of work to do. The importance of what you're studying still will certainly matter. Okay, again, zooming in on Bellingham. This is per capita emissions. So you take all those emissions, those 1 million metric tons, and divide it by the 100,000 people that live here. And so each of us are responsible for a certain amount of CO2, and most of that for people that live in Bellingham comes from their transportation, comes from burning gasoline and diesel in their cars. Okay. So this equation should be pretty familiar to you now. Greenhouse gas accounting for transportation is actually pretty easy. It's how much fuel you consume multiplied by the carbon intensity of that fuel gives you the mass of CO2. So this equation is a function of two variables. What do you think these two variables will be a function of? Let's start with fuel. How much fuel will we need? What will that depend on?
Distance shipped or traveled?
Yeah. How far you're shipping something, how far you're driving. So there's a metric called vehicle miles traveled. And average vehicle mile traveled for a person in the United States is about 12,000 miles a year. How much fuel will also depend on the efficiency of your car. So I'm seeing MPG, distance, and efficiency up on the chat. So yeah, all those things. How efficient is your vehicle? How far are you traveling? What will the carbon intensity depend on?
It's the chemical properties of the fuel.
Yeah, are you burning biodiesel? Are you burning ethanol? Are you burning gasoline? Are you burning diesel? Or are you consuming electricity? And then you have to think about the carbon intensity of that electricity. All right, so the accounting, scope 1 for personal and company-owned vehicles. So this is scope 1 because it's smoke coming out of a smokestack, right, or from a tailpipe. And then it's scope 3 for transportation of goods and resources and supplies. So if you own a store or a restaurant and you're shipping things in, those would be scope 3 emissions. And with the advent of electric vehicles, we now have to think about scope 2. So there's no tailpipe emissions, but you have to charge that vehicle. So now there's scope 2 emissions for electric vehicles. Cool. All right, yeah, so how much fuel, efficiency, mode, and speed of transportation. The efficiency is usually measured in things like miles per gallon for gasoline and diesel, kilowatt hours per mile or kilometer for electric vehicles. So how many kilowatt hours do you need to put in to go a mile? It's flipped from miles per gallon, right? Miles per gallon is what you get over what you pay. You pay a gallon, you get some miles. Kilowatt hours per mile is like an energy intensity rather than an energy efficiency. How many kilowatt hours do you have to put into that car to go a mile? And then you're familiar with this from the bubble water homework. When you're shipping goods, it's gallons per ton mile or kilometer or ton kilometer, that sort of thing. Okay, and then carbon intensity depends on what we're burning. You guys got that. And if it's an EV, it depends on what you're charging the battery with. Okay, so here are some carbon intensity of different transportation fuels. This is lifted from the EIA.gov, Energy Information Agency, so everything's in American units. And so we have pounds of CO2. Thankfully, they put kilograms of CO2. And this is per volume or mass of fuel. So if you look at gasoline down here, it's 8.89 per gallon. Incidentally, this is the direct emission. So if you light a gallon of gasoline on fire, you will spit out 8.89 kilograms of CO2. But if you take into account the so-called wells to wheel emissions, so emissions associated with producing the gas, producing the oil, distilling it into gas, and then transporting it to the gas station, this total 8.89 goes up to 12.12 CO2 equivalent per gallon. So that also accounts for some methane that's emitted with the higher global warming potential of 25 to 30 or whatever. So this is the one you should use in your analysis because this is what everybody uses, but the real picture is actually worse than this. So you can, as a subnote, say that actually it's like this instead of this 8.89. Diesel is 10.16 kilograms of CO2 per gallon, so higher than gasoline. There's more energy in diesel. There's more carbon, there's more hydrogen, and so there's more emissions per gallon. But you also have more energy per gallon, and so that's why diesel vehicles achieve higher mile per gallon, just because there's more energy there. But because there's more energy, there's also more emissions. Let's see, anything else? Yeah, that's pretty good. Oh, jet fuel, 9.57 per gallon. Aviation gas, 8.35 per gallon. So aviation is for prop airplanes, jet is for jets. Okay. When we're transporting people, we think of vehicle miles or passenger miles. And so here's, this is from the EPA, Environmental Protection Agency, and they have CO2 factor, methane factor, and NOx, nitrogen oxide factors for vehicle miles for a passenger car. And so looking at CO2, it's like what, 0.36 or something, 0.37 kilograms per vehicle mile. And then you can go down to air travel. So this would be like domestic air travel, traveling to New York or something. It's about half. And so a couple things to point out here. Air travel is a more efficient way, a lower emission way to travel than driving. The reason why your personal emissions go so high if you just take one flight per year, is because you're going a really far way. You're going a long way. You're going 2,000 miles or something. And so even though it's more efficient emits less than a passenger car, because you're going so far, then that's why you get this big hit to your personal carbon budget. Another thing to point out, notice this is about half of this. And so if you carpool or you have one other person in your car, your emissions per vehicle mile are the same, but your emissions per passenger mile are now cut in half. So as soon as you have one person in your car, it's the same as air travel. And if you go on a road trip with your friends down to California or something with 4 of you in the car, then it's less emissions per person than traveling in an airplane. It also takes 18 hours instead of 2, but it's kind of fun, right? So if you want to lower your emissions in a passenger car below that of an airplane, just have 3 people in the car or have an electric vehicle. Okay. Light duty trucks, your Ford F-150 is worse than a passenger car. That's kind of obvious. Motorcycles are less heavy, so it's lower. And then here's some different passenger mile emissions for different types of transport. Bus is a tricky one. An empty bus is going to be way, way worse than a car. And unfortunately, Bellingham seems to have pretty full buses, but other cities I've lived in, like Shallow, Alto, nobody's riding the bus, but the buses are still going around everywhere, and that's a waste of energy, resources, and emissions. Okay, so that's for people. Transporting goods, the unit you want now is ton miles. Again, this is from the EPA. It's an American site, so it's short tons, 2,000 pounds, which is a little bit less than 1,000 kilograms. So you have to do a little factor there. And so moving things by truck. I love the trucks in India. They always pimp them out like crazy. Shipping, and then air travel. So per ton mile, let's not do vehicle mile. If we look at medium and heavy truck, it's 0.3 kilograms per ton mile. Rail, factor of 10 less. Rail is super efficient because there's several reasons, right? Not nearly as much friction. Instead of rubber on asphalt, we have metal on metal, which is actually quite efficient. Not much friction at all there. There's far less stop and go, and it travels at a speed specifically tuned at the highest efficiency curve of the engine driving the train. So they get up to 80 miles an hour, and the engines are designed such that they are most efficient at 80 miles per hour. And so trains are super efficient. Waterborne craft, much more efficient than trucks. Again, it's just the friction is way down, and they can take advantage of ocean currents, and again, the engine runs at a perfect peak of the efficiency curve, whereas a semi-truck on the freeway is always speeding up and slowing down. To make trucks more efficient on the freeway, they're doing things like trying to keep their speed constant by turning trucks essentially into trains, have automated controls and automated LiDAR sensors or infrared sensors on the trucks to keep them all about 5 feet apart, and so they can draft off each other and all maintain the same speed, and so several trucks in a row can turn into a train. So these are some ideas going forward for truck travel. So all of these things could be interesting project ideas for this class. You could think about how many trucks are going between here and Seattle transporting goods, or wherever the nearest FedEx warehouse is, or UPS warehouse. I think they're probably all down in South Seattle, right, where all those warehouses are. You think about how to, I don't know, it'd be an involved project, but it's something that's interesting. Okay, moving on to electric vehicle emissions. Emissions, again, depend on the efficiency of the vehicle. That's the fuel component of that equation at the beginning of the lecture. And then the carbon intensity of the charging source. So how intensive is the electricity that's charging the vehicle? And so this is from some of the analysis that Patrick, UTA, has been doing for the city of Bellingham. And we can look at internal combustion miles per gallon. On average, it's about 22 miles per gallon for a passenger car. Gasoline, carbon intensity is again 8.89 kilograms per gallon, kilogram CO2. I'm going to move this camera a little bit. So if you take these two numbers, 22 miles per gallon and kilograms per gallon, take this divided by 22, and we get 0.404 kilograms per mile for a passenger vehicle. Okay, so let's look at the electric vehicle equivalent. So it depends on the efficiency of the vehicle and the charging source. So the charging source is Puget Sound Energy. I didn't list it here, but it is at about 427 grams per kilowatt hour, 0.427 kilograms per kilowatt hour. So that's the carbon intensity for PSE. I have it on a later slide, so don't freak out. And then these are the efficiencies of the different, or the energy intensities, I should say, because it's not get over pay, it's pay over get. For a Tesla 90D, so this is one of the actually least efficient electric vehicles because it's the super fast one, right? Has so-called ludicrous mode or whatever. But it's still really efficient compared to internal combustion car because there's way less entropic losses because you're going from electricity to mechanical rather than chemical to heat to mechanical. And it can take advantage of things like regenerative braking, right? So when an internal combustion engine slows down, you make heat and brake dust. When an electric car slows down, you make You spin a magnet, which drives a current, which can recharge your battery. A Nissan Leaf is slightly more efficient than the Tesla S90D, and then projected 2020 efficiency. So when Patrick was doing this analysis last year, the projected efficiency was 25 kilowatt hours per mile. This has already been beat. The 2020 Tesla 3, which is the more economy class Tesla, has a energy intensity of only 0.24 kilowatt hours per mile, and that's something great about EV tech, right? It's relatively new, so it's going to get better and better and better rapidly, especially compared to internal combustion engines, which have been around for 100 years. And so if you look at the CO2, kilograms of CO2 per mile for EVs, for the internal combustion, it's 0.4 kilograms per mile. For Tesla S90D, it's a factor of 3 or 2 to 3 less. And then for the Tesla 3, it's a factor of 4 less. So it's pretty amazing. And that's with PSE's grid, which is not the best. It's kind of around the US average, but it's terrible compared to the Washington State average, which is around 0.1 to 0.2 kilograms of CO2 per kilowatt hour. So these factors would all be cut in half or more if we had Bonneville grid. Okay, so the EV efficiency depends on the mass of the vehicle principally. And so this Tesla Cybertruck's going to do way worse than the Tesla 3. These values aren't out yet. Aerodynamics, again, Tesla Cybertruck's not going to do the best. Tires, again, Tesla Cybertruck's not going to do the best. Tires is friction, right, against the road. Aerodynamics is friction against the air. And then mass is going to be a component of both those friction forces. Battery charge discharge efficiency, so that depends on the quality of the battery and the inverter and all that sort of thing. So how much electricity actually goes into the battery and how much electricity actually comes out of the battery without producing side chemical reactions and waste heat. Does the vehicle have regenerative braking or not? And then obviously driver behavior, which is important for all types of vehicles. If you're driving recklessly or flooring it and stopping all the time, then your efficiency is going to go way down. You can get fuel economy for almost any car from this link down here at the bottom of the slideshow, fueleconomy.gov. It's a product of the Department of Energy. Okay, so this new movie by Michael Moore just came out, Planet of the Humans or something. I used to have a lot of respect for that guy, but he really screwed up with this last movie. I don't know if he's been living in rural Michigan for too long or what, but a lot of the data is at least 10 to 15 years old, and the analysis was more like, evocative and gotcha rather than factual. I only got through about half of it before I got too pissed off. I couldn't continue. There's a lot of good articles about it. Bill McKibben wrote something in Rolling Stone. Leah Stokes down at UC Santa Barbara wrote a good article on Vox about the movie. So if you watch it, know that it sucks. And if your friends or parents or something talk to you about it, tell them that it sucks. One of the things they said in that movie is that switching to EVs isn't even a good idea because it's still polluting because you have to charge it with electricity. Yes, thank you for that preliminary analysis, but let's count. Let's use our mathematical capabilities and see how much CO2 is actually produced by these different things. And so, building on the analysis from the last slide, carbon emissions depend on fuel and carbon intensity of that fuel. How much fuel you use and the carbon intensity of that fuel. How much fuel you use depends on the efficiency of the vehicle, and the carbon intensity depends on whether you're burning gasoline or electricity, and the carbon intensity of electricity depends on where that electricity is coming from. So this has the carbon intensity of a power grid, kilograms per kilowatt hour. National average, it's about 0.5 kilograms per kilowatt hour. That's what you get from burning natural gas. If you have more coal in your grid mix, then you start approaching these higher nut values. If you're burning pure coal, you're going to get 1.25 kilograms per kilowatt hour. If you start blending natural gas with nuclear or renewables, then you'll start achieving values less than 0.5. So PSE is a mix of a little bit of coal, mainly natural gas, and then a lot of hydro. So that's why we're at about 0.4. It's kind of like we're hydro plus coal and then balanced by natural gas. So that's why we're near natural gas. Right now, PSE is phasing out their coal plants. They've already phased out, I think, 2 generators. And so expect PSE values by next year to get around 0.2, because now it's going to be a blend of hydro and natural gas rather than hydro and coal. 0.2 is what Seattle City Light is. Seattle City Light is more like 0.15. A lot of California is down to like 0.25 because it's a blend of natural gas and solar power. And then the best, the cleanest power grids like Snohomish County Power Grid and Chelan County Power Grid, which are nearly 100% renewables, they're around 0.1 or 0.5. Okay, so if you charge a electric vehicle with a average electric vehicle efficiency, recall the Tesla 3 is now better than this. It's at 0.24 kilowatt hours per mile. You'll only put in 0.24 kilowatt hours to get a mile, but the average electric vehicle fleet today is about 0.3 kilowatt hours per mile. So if you charge that with the average US grid at 0.5 kilograms per kilowatt hour, you get 0.15 kilograms of CO2 per mile. If we compare this to the average mile per gallon of an internal combustion car of 22 miles per gallon, and we assume that the gasoline is just direct emissions of 8.89 kilograms per gallon, then we have 0.4 kilograms of CO2 per mile. So average grid, average EV is 0.15, average car, and not even accounting for extra emissions due to gasoline, is 0.4. So it's already over twice as good as a average car in America. If you take into account the well-to-wheel emissions, then it's 3 times as good, 0.15 to 0.5. Okay, somebody says, well, what if I have a super efficient car that I drive like, okay, I won't make any kind of like judgments on age. Okay, you drive very carefully. And you have a Prius. So say it's like 44 miles per gallon, 48 miles per gallon. That's if you're driving a Prius perfectly. And again, that kind of has a battery in it. Then you're at 0.19. So that's still worse than the average EV with the average grid. So what kind of power grid do you have to have before a Prius gets better? You need to have a blend of about half gas, half coal. And so yes, there are some counties, some regions of America where a Prius is equivalent to an EV. If you're driving an EV in the worst places in America, so like a grid in rural Wyoming or Kentucky, and that's not disparaging those states, those are just very coal-heavy locations, then yes, driving an EV, charging it purely with coal is still better than the average car, but far worse than a Prius, okay? So I guess if you live in Kentucky, rural Kentucky, drive a Prius, but good luck making friends. Point of this is Michael Moore sucks at greenhouse gas accounting. You're better than him. Okay, let's look at some of the financing. Internal combustion engines versus electric vehicles. Did you guys see this video last fall when they had a Cybertruck fight a Ford F-150 towing, and the Cybertruck was even kind of going uphill, and it still won? It didn't win because it's like more powerful or anything like that. It only won because it's so much heavier. It's like 3 times heavier. So the coefficient of friction of the Tesla Cybertruck against the ground was like 3x the coefficient of friction of the Ford on the ground. And so it just kind of cheated because the Ford would skid because it didn't have nearly as much load. But anyway, what they should have done is like tow the same load in the same direction and see who wins. I still think the Cybertruck would have won, but this was a physicist's trick, this experiment here. Okay, so this is taken from Puget Sound Energy's website. They have this cool little tool to look at how much you'll save by switching to an electric vehicle. They don't have a cool tool that shows how much you save if you switch from a natural gas water heater to a heat pump water heater, and that's because they're in the business of selling natural gas. But they are not in the business of selling gasoline, and so they're happy to tell you how much money you will save if you stop paying money to gas stations and instead pay money to PSE. And you will truly save money if you switch to an EV. So how far does $3.60 drive your car? If you have a brand new, so it has these drop down menus, you can type in what car. And so I tried to pick a very efficient non-hybrid car. And so Honda Civic 4-door automatic 2020, it achieves 32 miles per gallon. And so at a price of $3.60, that'll get you 32 miles. 32 miles per gallon will get you 32 miles. Duh. If you put $3.60 of electricity into your electric vehicle, I mean, that'll give you, 36 kilowatt hours or whatever. That'll take you 141 miles. And that's an efficiency of 0.256 per kilowatt hour. I don't know why their efficiency for their intensity for the 2020 Tesla Model 3 is higher than the actual spec sheet intensity for the Tesla Model 3, but it's not too different, 0.24 versus 0.256. So $2.60 will get you 4 times as far in an EV versus a gas powered. So operating costs are a factor of 4 better for an electric vehicle. If you drive 50,000 miles per year, this is what that tool at PSC's site assumes. How much money do you save over the course of 5 years? A gasoline powered car will cost you $1,687, and that's a very efficient one. So a truck would cost you twice that, for example, versus $384 per year for the EV. Over 5 years, you just multiply these numbers by 5. That's what the tool does. So over 5 years, you'll save $6,500 by having a Tesla 3 versus a 4-door Honda. And they're comparably priced. They're both about $30,000 new. Okay, not everybody has $30,000. Most people don't have $30,000. So let's look at a more affordable option. So yeah, when I gave this presentation to the YWCA here in Bellingham back in February, back when people could be in the same room, and an older person got really upset and said, like, I can't afford a Tesla 3, so like your analysis is silly, like why are we even doing this? And she had a good point. We can't save the planet if nobody can afford to do it. And so let's look at a more affordable option. So that's what motivated me to make these slides. So let's look at used cars. So I just pulled these up on Craigslist last night when I was making this slide, and you can get a used Leaf, early 2010s Leaf, for about $8,000. And for that same $8,000, you can get a mid-2010s Elantra, which is also kind of an economy class car, smaller, but has some of the same creature comforts as the Leaf. So these are both relatively pretty nice used cars, right? And so this is what you can get for $8,000 instead of $30,000. Say you finance it at the used car lot. You have good credit, so you can get a 5-year loan at 2%. Assume gas at $3 a gallon, which is really low historically, but high in the COVID era when we have negative oil prices and nobody's driving anywhere. So I tried to give the internal combustion car the benefit of the doubt at only $3 a gallon per gasoline, even though I don't think that's realistic, certainly not in the past and probably not going forward. So this is all the tools we've been using throughout the class. We need to annualize these payments. And so to annualize a payment, you take the capital cost, $8,000. It's the same for both, multiplied by the cost recovery factor. And what does that cost recovery factor do? It spreads those payments out over the life of the loan or the life of the technology. And so if it had a 0% discount rate or interest rate, it'd just be 8,000 divided by 5 because that loan lasts 5 years. But you have to pay interest on that loan. And people value money today more than later. And so it has this funny setup where you have this interest component in addition to the annual component. And so instead of having to pay $8,000 divided by 5, which I don't know what that is, you have to pay a little bit more. $1,697.27 per year to finance that loan over the course of 5 years. Okay, so that means that to drive this car, you have to pay that car dealership $1,697.27 every year. That's the same for the Leaf as it is for the Elantra, because I said they cost the same and you have the same good credit, same loan terms. Okay, so the annualized payments for CapEx are the same. What about operational costs? Operational cost depends on how much fuel you consume and the price of that fuel. So I assume both cars go 10,000 miles per year. The efficiency of the Leaf is 0.3 kilowatt hours per mile, and it costs 10 cents per kilowatt hour. And so to charge that Leaf with electricity will cost you $300 a year. Total annual cost, assuming no maintenance, is $1,997. For the Elantra, 10,000 miles a year again, 28 miles per gallon. If you look it up on the internet, $3 per gallon. Then you have to spend $1,071, so about 3x or more than 3x for the gasoline. So similar analysis that was shown in that PSE tool. So annual cost, no maintenance, $2,769. Actual maintenance for internal combustion engines are about 3x of electric vehicles. Electric vehicles, you just have to change the tires. You don't need oil because you don't need to keep your engine well lubricated. There isn't pistons exploding things all the time. Way fewer moving parts. And so, what is the battery life? Brooke just said, what is the battery life for the Leaf or general EVs? People assume about 10 years at 10,000 miles a year. In general, lithium-ion batteries last about 1,000 to 2,000 charges, but you only charge that vehicle every couple days or less. So there you go. And that's why your cell phone lasts about 2-3 years max. 1,000 divided by 365 days, you charge it every single day. Your battery sucks after 3 years. And that's why you start noticing your cell phone not being as good as it used to be 2 years out. And then 3 years, you're like, okay, this is really starting to bum me out. And you get a new one. Yeah, good question. So yeah, buying a 2010 Leaf might not be the best idea, but it depends on how many miles it has. Okay. So I favorably looked at emissions for both classes. I said PSE doesn't have coal anymore, so that's where they're going by the end of this year. So 0.2 kilograms CO2 per kilowatt hour. And gasoline is only direct emissions, no well emissions. And so 8.89 kilograms of CO2 per gallon. Metric tons of CO2 is fuel multiplied by carbon intensity, same for both. So for the Nissan Leaf, 10,000 miles multiplied by the fuel, which is, well, I guess this is the fuel here. So how many kilowatt hours multiplied by the mileage. And then the carbon intensity is right here. So 0.2 kilograms CO2 per kilowatt hour, convert from kilograms to metric tons, 0.6 metric tons. Same analysis for the Elantra, 10,000 miles. Here's the gas mileage. Here's the carbon intensity of the gas, converting from kilograms to metric tons. And it's way bigger. What would that be? Like 5 times. 5 times is great. 5 times as many emissions as the Leaf. Why? Gasoline is dirtier or emits much more than electricity, and the electric car is much more efficient than the gasoline powered car. Okay, getting another. Has anyone done a study looking at how much carbon is emitted during the mining, creating the battery, as well as creating the car? And yes, I have. Thank you very much. Yeah, a lot of people have. So the best one is Linda Gaines at Argonne National Laboratory. She has this whole battery lab where she takes apart batteries and analyzes she reverse engineers them and calculates their scope 3, their life cycle emissions. A more recent study that came out, I think Hiremath et al. Out of Germany in 2016, that has some good analysis. Yeah, I'll post some of those studies. Good question. But the overall like lifetime emissions, like the emissions from charging the car is like something like 95% of the emissions, and then you have about 5% emissions from the batteries. Another important question is what to do with the batteries at the end of the life. So nobody's answered that question yet. Right now, all the used batteries from EVs, Tesla takes them back and they turn them into power walls. They recondition them. But most all lithium-ion batteries from mirror devices, cell phones, laptops, lawn equipment, vacuums, and EVs, they're all being dumped in this massive warehouse in Calgary, Canada. I have no idea why. So the biggest problem with repurposing batteries is they all have different form factors, right? They all have different shapes. Like here's a lithium-ion battery in these stupid headphones. Here's a lithium battery in this phone. They all have different shapes, slightly different chemistries, different form factors. And so you can't like take them apart with a robot and sort them with a robot because it's all different. And it lacks standardization. So that's a big thrust right now in that industry. And it's honestly like a pretty good industry to get into if you're, I know batteries aren't the most interesting thing, but it'd be lucrative, and it's a huge problem right now, trying to figure out what to do with batteries at the end of life. Basically, we need a standard. Right now in America, you can plug anything into a plug anywhere, and that's a international standard plug, right? Some people got together and said, all plugs will look like this. They'll have this shape. They'll all have 120 volts, and they'll all have 15 amps. And no matter what we plug in, it'll be the same. Right now, that's not the case with batteries. And so if you have some homogeneous ecosystem like Tesla does, then yes, you can recycle them or repurpose them. But nationwide, globally, we're in the weeds here. Every battery is different, so we can't figure out what to do with them. There's some funny videos, again at Argonne National Lab, funny, haha, of batteries exploding. They're trying to take them apart and recycle them. But, you put in the wrong lithium ion chemistry, because you have like lithium ion, lithium phosphate, lithium cobalt. You put in the wrong flavor, it's going to explode, right? And so luckily nobody got hurt in those videos, except the robot, I guess. All right, good question. So let's calculate the MAC. Marginal abatement cost is dollars per metric ton of CO2 abated. To calculate the cost, you take the project, which is usually more expensive than the baseline. And then for the denominator, you want to see how many tons of CO2 you save. So you take the CO2 you were emitting, baseline, minus project. So cost is project minus baseline. CO2 is baseline minus project. Put in these annualized costs for project minus baseline. They had the same capital cost, but the operating cost of the Elantra was greater because the gasoline cost more. And then the difference in baseline emissions from project emissions, and we have a negative MAC for switching to EVs. So you save money and carbon if you switch from a internal combustion engine to a EV. But that capital cost sucks, right? I haven't done it yet just because, I bought one car in my life when I turned 30 something, and it still works, and I don't want to, and it's paid for, so I don't want to pay for a new car yet. But as soon as it dies, I'll definitely get an EV. This coronavirus, I don't even drive anywhere anymore. My car didn't start anymore because I hadn't run it in like 5 weeks. I didn't really care. Okay. So how do we get better transport? David McKay, you've probably seen this book from some of my other classes, Sustainability Without the Hot Air. It's free at withouthotair.com. It has a few different maxims. So in short distance travel, so like going around towns, lots of starting and stopping, the energy mainly goes into speeding up the vehicle and its contents. Key strategies for consuming less in this short transportation are therefore to weigh less and go further between stops. So drive better. Regenerative braking, so drive an EV with regenerative braking is a big thing. Captures energy when slowing down, help too. And then move slower, move less. So walk, ride a bike, consolidate your trips. Long distance travel, it's more important to travel at a steady speed. So trains or automobiles going long distances, most of the energy goes into pushing the air out of the way. You're driving 60 miles an hour, you're colliding with air that's going 0 miles an hour. That's an impact, right? A momentum impact. And so all of a sudden you have to make that air go 60 miles an hour to get it out of your way. And so that's where most all the energy goes into. So key strategies for consuming less in this sort of transportation: move slower, move less, use long, thin, aerodynamic vehicles. All forms of travel, there's this energy conversion chain. You know this from the second law of thermodynamics. So energy from some form gets transmitted into mechanical energy, pushing the vehicle forward. So look at that energy chain, make it shorter, make it more efficient. In standard fossil fuel car, only 25%. That's like a high estimate. I usually see like 22% is actually used for making the car go forward. Most of that energy is just lost, making the engine and radiator hot and swirling air all around. So the most obvious way to make that energy conversion chain way shorter is just electrify everything. And then you're just going from electricity to mechanical rather than chemical to heat to mechanical. And that's why electric vehicles are like 80% efficient compared to 22% efficient for ICE. All right, so 6 principles for vehicle design, and these are different things you could think about for your project. Change the shape, change the weight of the vehicle, go at a steady speed, avoid using brakes, travel more slowly, travel less, make the energy chain more efficient. All right, so a few charts from David McKay's book. I like this one. On the y-axis, it's energy consumption, so kilowatt hours, per 100 passenger kilometers. You can just think passenger kilometers, right? I think that per 100 made these numbers on the x-axis not look crazy. Okay, so it's energy consumption per passenger kilometer. And then on the x-axis is speed. You'd think in general, the faster you go, the energy per passenger kilometer would go down, but unfortunately, people have made some real stupid modes of transportation. Namely, the jet ski is... the Earth race is just a big jet ski. It's a 4-passenger jet ski. So jet skis are the least efficient vehicle humans have invented, pretty much. And that's because they just have a really short length. And the way boats work and ships work is they create a wave and surf that wave. And wave speed is proportional to wave length. And the jet ski can only make a teeny wave. And so it has to like continuously create that teeny wave to go forward. The longer a boat or ship is, the more efficient it is because it can surf much bigger wave. So general boats aren't the best, and then we get down into different types of airplanes. They go way faster, but they are far less efficient at moving than cars are. These different symbols represent full versus nearly empty. And so if you fill the plane up, you get much better efficiency per passenger mile. And then we start getting into ground transportation here. So electric trains are the most efficient. So this is like TVG in France and the high-speed rail in Japan and China. And then diesel high-speed rail is what we have in America and all over Europe, England, France, etc. And then electric cars are slightly better than diesel rail. So this is what we're looking at. Walking is here. The most efficient mode of transportation ever invented by a human being is a bicycle. It's more efficient than walking. I think that's pretty cool. Why is that the case? There's less friction, right? You don't have your shoes going. You just have a wheel rolling. And the skinnier that wheel is, the less friction you have, and that's why the Tour de France bikes have those hyper skinny wheels to make them as efficient as possible. This chart over on the right hand side shows it's a histogram. It's a little dated. It's from when this book came out back in 2011, but it's number of cars per sale, and this histogram shows the number of cars of a particular emission intensity on the road, which is a reflection of energy consumption. They're tied to each other, right? You're burning gasoline. The less efficient your car is, the higher the energy consumption is, and the more emissions you'll have. And so UK average is right here at 168 grams per kilometer, grams of CO2, and energy efficiency or intensity of about 70 kilowatt hours per 100 kilometers. So that's 0.7 kilowatt hours per kilometer, which would be 1.4 kilowatt hours per mile. And so it's four times as bad as an electric vehicle, which is identical to our analysis from the other slide. Okay, so you can see that the cooler the car is, the more emissions they make. That's the point of this chart. Ferraris make a lot of emissions. So do Audi 8s, A8s, compared to like an Audi A3, which is much, much smaller engine, much more efficient. I have no idea what a VW Polo Blue Motion is. Must be an English thing. Okay. Ride a bike. So you can look at some of these emissions, grams per kilometer. Average new car, here you have 160 grams per kilometer. In a bike with an average diet, you cut that down by a factor of 2 or greater. And this is a little disingenuous because you're still making CO2 as a human when you're driving your car. Yeah, you're not breathing as hard as the bicycle, but you're counting the human emissions here, whereas you aren't in the car analysis. Okay, if you have a vegan diet, you have less emissions associated with raising cattle, or not raising cattle, I should say. If you're a paleo diet, then you have more emissions associated with raising meat. And so it starts to get almost as bad as a car, as a Prius. And then by the time a typical car, it gets far worse. All right, bike infrastructure really matters though. People don't ride bikes in general because it takes longer, it's inconvenient, you get wet from the rain, or you sweat, or it just doesn't feel safe at all, or it's not convenient. So here's an example of terrible bike paths versus some better ones. So this is the bike infrastructure rebuild happening in Bellingham right now. So they redid the bike path on, what is this, Chestnut, I think, to make it much safer for bikers, increasing the visibility for bike use. Still kind of not the best planned thing because it goes right into a super steep hill. So you have to have like an e-bike or be in really good shape to be able to use this bike path. Here's the City of Bellingham Public Works plan for bike paths. So this could be another marginal abatement cost project you could do. You could think about, well, how much does it cost to install one of these bike paths, and how many people will opt to start riding their bike versus driving their car? And you could look at fuel prices for cost savings to offset the cost of the bike path, and then look at CO2 emissions. It'll take some thought, but it's a cool idea that you could look into. And so this chart shows future proposed bike paths. Blue is existing, green is recent improvements, magenta is planned improvements, and then the red is stuff you can't do anything about, right? freeway is in the way, and Lakeway is a very dangerous road for bicycles. All right, other ideas for your Mac project associated with transportation, check out Drawdown Solutions. So I'll do that right now. Let me get out of this slide. So hide that panel. Solutions, Drawdown. Okay, so if you go to drawdown.org/solutions, you can click transportation, and you get all these other ideas. So bicycle infrastructure, that's what I just talked about. Carpooling, efficient aviation, efficient ocean shipping, efficient trucks, electrifying bicycles. So that gets rid of the fitness barrier and the time barrier that goes with switching from cars to bikes. All of a sudden, it's easier to bike and they go faster. Switching to electric cars, we showed that in this lecture. Electric trains, high-speed rail, hybrid cars, public transportation, telepresence. I guess we're doing that right now. That could be an interesting analysis to do. Then walkable cities. So in the Bellingham Climate Action Task Force plan, there's this idea to get rid of all car traffic on Railroad Avenue and turn it into a park. And there could be more stalls and food trucks and stuff along the center there, and have all sorts of public artwork and activities, concerts, and that sort of thing along Railroad Avenue. How would that affect the emissions associated with the city and Railroad Avenue? There's been studies in Boulder, Colorado, and Burlington, Vermont, where they converted central city streets into walkable avenues, and they actually increase revenues and participation in all the businesses along those streets because it's a more desirable place to hang out, and people drive less and choose to bike to those locations. So that could be an interesting thing to look at. So this will give you some more ideas to play with. And again, I'm not expecting professional grade report or analysis out of this. I just want you to pick a cool idea and think about how much it costs and how much emissions will be saved. Okay, that's it for today. I'll hang out for 10 minutes or so, 5 minutes or so if you guys have any questions.
Sweet. Thank you, Charlie.
Yeah, my pleasure.
Thanks, Charlie.
Adios.
What time works to call, Charlie?
Now.
Okay, sounds good. I'm gonna make a little food and then give you a call.
Yeah, no worries.
Okay, sounds good.
Bye. All right, I'm signing off.